Section 1 Introduction. We're going to delve into the world of large, pre-trained language models, LMs, and how they've revolutionized the way we understand and generate language. These models have made it possible to tackle a wide range of complex tasks using a unified approach, eliminating the need for custom neural architectures. They've proven their worth by outperforming other methods on almost all standard benchmarks in natural language processing, NLP, and have been successfully used in popular applications like ChatGPT. While there's a lot of excitement around the ability of these large models to reason with little or no prior examples, a common approach to tackle specific NLP tasks is to take a pre-trained model and fine-tune it with data from the new task. As the model size increases, so does its performance. However, this comes with a downside. It requires a lot of computational resources during fine-tuning, even though it's less than what would be needed if we were to train the model from scratch. Moreover, fine-tuning is usually done for each new task separately, without considering any other tasks the model might have been used for before. This not only increases the computational cost for all tasks, but also misses out on the opportunity to share knowledge across tasks. In this study, we're looking at fine-tuning efficiency from a continuous learning perspective. We're asking, if we've already solved a number of previous tasks, can we use the knowledge gained from these tasks to solve the next task more efficiently? We're particularly interested in situations where each of the previous tasks has a large number of training examples, a scenario that's common but not well addressed by few-shot prompting. We hypothesize that the standard pre-trained model, which is commonly used as the starting point for any fine-tuning task, might not be the best choice. Instead, models that have been fine-tuned on one or more of the previous tasks might serve as better starting points. This is based on the assumption that knowledge transfer happens through parameter initialization. We're interested in how quickly our learning algorithm can produce good models for new tasks. Specifically, how much computational resources do we need to produce a model that performs at a certain level? Or, given a certain amount of computational resources, what's the best performance we can achieve? In the context of continuous learning, we're focused on forward transfer, which we define as learning a new task faster compared to our baseline strategy of independent fine-tuning from the original pre-trained LM parameters. Of course, the success of this approach depends not only on the algorithm used, but also on the relationship between the new task and the previous ones. We conducted a large-scale analysis of interactions between 55 popular and publicly available English language tasks using AT5LM. We found that the transfer landscape is quite complex. In some cases, pre-training on one task can speed up adaptation to another task, but in other cases, it can be detrimental. We argue that practical, efficient continuous learning requires algorithms that can handle the inevitable variations in the composition of the previous tasks. To this end, we've created a challenging benchmark of multiple task sequences that represent different possible scenarios, such as a sequence of tasks with high potential for positive transfer, high potential for negative transfer, no expected effect, or a mixture of each. We propose a simple method that meets many of our requirements. Specifically, we learn a model that can select the best checkpoint to start from, given some representation of the current task and all previously seen tasks. This includes the option to start from the pre-trained model, which is what a standard fine-tuning approach would do. We show that training a lightweight decision tree on top of features of each task over a small collection of held-out task pairs with different transfer relationships can result in good selection performance on new tasks, especially when there are past tasks that are best ignored. In summary, our work contributes to the field in 3 ways. 1. We explore the concept of continuous learning for efficient LM fine-tuning and forward transfer. 2. We present a large-scale analysis of task transfer interactions and a new benchmark of task sequences that capture diverse potential transfer profiles. 3. We propose a simple but effective method for checkpoint selection and model initialization that enables more robust forward transfer. Section summary. Recent advances in large, pre-trained language models have revolutionized language understanding and generation tasks. While fine-tuning these models on new tasks is effective, it incurs significant computational costs and fails to leverage knowledge from previous tasks. In this work, we propose a method for efficient fine-tuning and forward transfer by selecting the best checkpoint from previous tasks, based on a large-scale analysis of task interactions and a benchmark of task sequences. This approach enables more robust and computationally efficient learning on new tasks. Section 2 Related work. Our research builds upon a significant amount of recent work that aims to enhance the efficiency of training contemporary language models through a process known as forward transfer. This involves using the parameters from a previously trained model as a starting point. Specifically, we're interested in how data from auxiliary tasks can be used to improve the performance of a target task. This has been a hot topic in research for several years. Our approach falls into the category of intermediate fine-tuning. In this process, a model is initially trained on an auxiliary task, let's call it task A, before being applied to a target task, task B. This approach has been thoroughly examined in a pairwise setting, meaning only transferring from task A to task B. Previous studies have provided practical guidelines on how to choose the best pair of tasks for transfer. In our work, we're expanding this pairwise training to include full sequences of intermediate tasks that are continually learned. The main focus of our work is on continual learning for efficient language learning. Continual learning has been a topic of great interest in the machine learning community over the past decade. Existing methodologies for continual learning can be broadly divided into three categories: replay-based, regularization-based, and architecture-based approaches. Many of these methods aim to achieve efficient forward transfer of parameters and to avoid catastrophic forgetting. However, our interest lies solely in improving training efficiency for new tasks. We're not concerned about how performance might decline on previous tasks. Instead, we're focusing on different strategies for initializing the model. This is based on our assumptions that we know which task we're trying to solve at any given time and that we can save and load previous models when needed. Our work also contributes to the growing body of continual learning datasets and analysis techniques for natural language processing, NLP. We're particularly interested in sequences that have a challenging structure and test for robustness against negative transfer. Section Summary. This section discusses two related areas of research: forward transfer and continual learning. Forward transfer involves training a model on an auxiliary task before transferring it to a target task, and previous studies have provided guidelines for selecting optimal transfer pairs. Continual learning focuses on efficient language learning and can be categorized into replay-based, regularization-based, or architecture-based approaches. In this work, the authors focus on training efficiency for new tasks and different model initialization strategies, without considering performance on previous tasks. Section: Efficient Training for NLP. Our research is closely linked to the efficient training of language models, which includes aspects like parameter reuse and model size. Although we don't focus on these aspects in this study, they can complement the type of training efficiency we are concentrating on. The metrics and analysis we propose might also be of independent interest. Let's define our language model, which we'll denote as LM_theta. This model generates natural language responses, Y, based on a given prompt, X. For our experiments, we use the pre-trained T5 base model, specifically the version adapted for language modeling. During the fine-tuning process, the model parameters change based on the number of update steps, n, that have been taken. We denote this as thetas. We measure the performance of our updating language model, LM_thetas, by its lowest loss achieved within a budget of B update steps. This is represented as perf. B. To simplify things and avoid confusion between different implementations, we use the same model architecture, batch size, and learning rates in all our experiments. As a result, the number of update steps is directly related to the total training cost of the model, and improving perf. B simply means finding a better starting point for our model, i.e., a choice of theta, 0, that leads to efficient trajectories thetas. An interesting future research direction could be to investigate how our findings apply to different types of models or learning algorithms. We also evaluate the area under the performance curve as a function of log updates, up to a maximum number of updates B_max. This is represented as perf AUC, B_max. This will be our main metric for comparing methods. We set B_max to 10K, which is typically the point at which most models for our tasks have nearly converged. Specifically, we're interested in comparing the efficiency of continual learning methods to the baseline of independent fine-tuning, where we always start from the same general pre-trained model for each task. We calculate this relative score as the difference between the perf AUC, B_max, of the independent method and the perf AUC, B_max, of the method, divided by the difference between the perf AUC, B_max, of the independent method and the lower bound for perf AUC, B_max. This score measures the relative improvement in terms of how much the compared method reduces the performance gap to the oracle, i.e., perfect prediction starting from step 0. Section Summary. The section discusses efficient training in natural language processing, NLP, and its relation to parameter reuse and model size. The authors propose metrics and analysis that can be of independent interest. They use a pre-trained T5 base model for their experiments and quantify the performance of the updating language model based on the minimum loss achieved within a given number of update steps. They evaluate the relative efficiency of different methods compared to independent fine-tuning and compute a relative score to measure the improvement in reducing the performance gap to the oracle. Section: 3.2 Sequential fine-tuning. We'll now explain a simple method for continual learning, which we'll use throughout the rest of this paper. This method, called sequential fine-tuning, is used on a series of tasks, one after the other. We start with a pre-trained language model and then adapt it for each task in the series. The model used for each task is initialized using the model learned from the previous task. To clarify, we use the symbol theta with a subscript I to represent the parameters for each task. We also use theta with a subscript I and a function of s to represent the parameters as they change with each update. We keep the model architecture, batch size, and learning rate consistent for each task. The only thing that changes is how we initialize the model. The simplest way to do sequential fine-tuning is to use the most recent model parameters, represented by theta with a subscript of I-1. However, this method isn't always the best, because the parameters learned for one task might not be a good starting point for the next task. In the following section, we'll discuss when the parameters from one task might be a good starting point for the next task, and when they might not be. To understand how well the parameters learned from one language task perform when used as a starting point for a new language task, we conducted a large-scale analysis on various pairs of language tasks. This is the simplest scenario in which sequential fine-tuning can be applied. The tasks we analyzed are shown in a figure and are similar to those used by Flan, but without translation. We grouped the tasks into task families to guide our analysis, but we're ultimately interested in how well the parameters transfer between individual tasks. To identify pairs of tasks that have either significantly positive or negative effects on each other, we use the following strategy. 1. We evaluated all possible pairs of 16 task families. For each pair, we first trained a model on a mixture of all tasks in the first family, and then used that model as a starting point for training a second model on a mixture of all tasks in the second family. Each model was trained on a balanced mixture of task data and evaluated based on the average performance across tasks within each family. 2. For each pair of task families, the average performance after sequential fine-tuning can be better, worse, or about the same as training independently. We used this information to identify individual tasks within the families that might show a similar trend. 3. For each task family, we identified the top 3 and bottom 3 families that transferred best and worst, respectively, to the original family. We then evaluated all individual task pairs within these families. In total, we evaluated 1757 unique task pairs. The results, shown in a figure, indicate that while many tasks show no significant effect from sequential fine-tuning, there are significant instances of both positive and negative transfer. However, this distribution is somewhat skewed due to our search and evaluation strategy. Despite this, we can still conclude that there are substantial numbers of both positive and negative instances. Section summary. In this section, the authors describe a simple continual learning procedure called sequential fine-tuning, where a pre-trained language model is adapted for a stream of tasks one after the other. The authors acknowledge that the naive implementation of sequential fine-tuning, which selects the most recent checkpoint as the initialization for the next task, may not always be optimal. In the next section, the authors conduct a large-scale analysis to understand the transfer potential between different language tasks and identify instances of both positive and negative transfer. Section 4.2 Types of transfer profiles. We're going to discuss the different types of transfer profiles that can occur in models. Some models show strong transfer from the get-go, meaning they perform well even without any prior exposure, zero-shot performance, and continue to improve. However, good zero-shot performance doesn't always predict future success. Some models start off strong but improve at a slower pace. Other models show no noticeable difference in performance. There's also a lot of variation depending on the task. Some tasks act as universal donors, meaning they positively transfer to most other tasks. Other tasks result in negative or minimal positive transfer. For instance, in our experiments, 73% of models that were first trained on the STSB dataset showed more than a 5% increase in performance across evaluated target tasks. Conversely, 70% of models first trained on the math dataset showed less than a 5% decrease in performance across evaluated target tasks. Understanding why these transfer curves form the way they do is complex and is a topic we're leaving for future research. However, these empirical phenomena allow us to create challenging sequences of tasks for continual learning. Ideally, a learner should be able to use information from all tasks that have potential for positive transfer, while avoiding tasks that could have negative effects. The learner should be indifferent to the mechanism causing the positive or negative transfer, which in many cases may not be well understood. We're using the pairwise transfer results to create a series of diverse, diagnostic task sequences. We categorize the pairs of tasks into positive, negative, and neutral subsets based on their relative performance to the independent fine-tuning baseline. For positive or negative tasks, we try to account for variance in training by requiring that the minimum or maximum relative performance results across all random trials are above or below 5%, respectively. We then construct 8 different types of triplets, where each of the preceding tasks are mostly positive, negative, or neutral pairwise transfer sources for the target task. We exclude the neutral case. For each configuration, we include multiple sets of triplets with different source and target tasks, and measure the median performance across task instances in all experiments. Specifically, on the test split of the benchmark, for each type of triplet, for example, positive, we include 4 distinct target tasks, each with 4 distinct preceding task pairs, for a total of 16 triplets per setting, and 128 triplets in total. More details are provided in the appendix. Section Summary. The section discusses different types of transfer profiles that arise in models, where some exhibit strong transfer from the beginning, while others start with better performance but improve more slowly. There is also significant variation across tasks, with some acting as universal donors, with positive transfer to most other tasks, while others result in negative or minimal positive transfer. The authors construct diverse diagnostic task sequences based on pairwise transfer results to create challenging sequences of tasks for continual learning. Section 5. Learning a checkpoint selector. We're now going to introduce a simple yet effective method for robust forward transfer, which we'll call a checkpoint selector. This idea is inspired by our previous analysis and a simplified version of a question we asked earlier. Here's the question. Imagine we have a set of tasks that we've already solved. Let's call them tasks 1 to n. Each of these tasks has a trained model. Let's call them theta. Now, suppose some of these tasks and their models are good starting points for a new task, task n plus 1. Given certain features of these tasks, can we train a discriminator, which we'll call d, to identify which of these tasks would be beneficial to use as a starting point for learning task n plus 1? In practical terms, when we're training a new model for task n plus 1, we want to be able to choose a model from a previous task to start from, if we believe it will help us. If there are multiple tasks that could help, we choose the one we're most confident about, using confidence scores from a model we'll call C. This model is usually the same as D, but without a decision threshold. If we're not sure that any previous task will help, we start from a pre-trained language model. We call this process selective sequential fine-tuning. It's similar to previous work on checkpoint selection for transfer learning, but with the added step of only selecting tasks that pass a decision threshold. We repeat this process for each new task. For example, for a sequence of tasks A to B to C, we start task A from the pre-trained model, task B from either the pre-trained model or the checkpoint for A, and task C from either the pre-trained model or the checkpoints for A or B in general. There are 2 to the power of n possible paths to take from the initial task to task n plus 1. We use a simple gradient-boosted decision tree, GBDT, for D, which operates on several lightweight, meta, features of an input task pair. C is the pre-binarized decision function of the GBDT. The GBDT is trained over positive and negative pairs from the training split of our benchmark. While we're not considering it in this work, it's worth noting that this process introduces a shift in distribution at test time, since the candidate models are products of multiple iterations of this selection algorithm, rather than only pairwise transfer instances. The features we use are fairly conventional and include metadata such as whether any of the previous tasks are in the same family as the new task, the zero-shot and few-shot performance of the model on the new task, and a number of gradient-based similarity metrics comparing updates to the old and new tasks relative to a starting point. Finally, we binarize D by setting a threshold for the GBDT confidence at 0.5. In other words, we only consider a checkpoint to be a candidate for selection if our model judges it to be more likely than not to be a positive transfer pair. Section Summary. The authors propose a method called selective sequential fine-tuning for robust forward transfer in transfer learning. They use a gradient-boosted decision tree, GBDT, as a discriminator to identify previously fine-tuned models that can act as good initializations for a new task. The GBDT operates on meta-features of task pairs and is trained on positive and negative pairs from a benchmark dataset. Section 6 Results. In Section 6, we present our findings. We've compared 3 different methods: the basic sequential fine-tuning, our own selective sequential fine-tuning process, and a theoretical ideal checkpoint selection algorithm. These comparisons were made across various task sequences in our benchmark. Our findings are summarized in a table, with additional details in the appendix. The theoretical ideal, or oracle, selects the most effective sequential fine-tuning path from the start point, t underscore 0, to the endpoint, t underscore n plus 1, knowing the outcome in advance. This oracle serves as a benchmark for the best possible performance of our selective model. In our experiments, we had 2 intermediate steps, n equals 2, which resulted in 4 possible paths. We present the median relative performance, perf AUC, across all 16 triplets for each sequence type. For example, we consider a sequence where task A leads to task B, which then leads to task C. Here, the transition from A to B results in a positive impact, while the transition from B to C has a negative impact. In the table, sequences with potential for positive impact are highlighted in green. When both tasks A and B have a positive impact on task C, continuing to fine-tune the sequence from A to B to C usually results in a positive impact. Interestingly, this impact is often greater than just transitioning from A to C or B to C. However, when a positive task is paired with a negative task, highlighted in red, the performance of the basic sequential fine-tuning is affected by their order. It performs better when the most recent task has a positive impact. Our selective method, on the other hand, can take advantage of positive impacts regardless of the order, although it can sometimes fall short of the oracle's performance. Sequences with potential for negative impact are highlighted in red in the table. Thankfully, unlike sequences with positive impacts, the negative effects from 2 negative or neutral tasks A and B don't usually add up. In fact, the negative impact can sometimes be lessened. In situations where there are no tasks with positive impacts to transfer from, our selective algorithm successfully chooses the pre-trained model as a starting point. This results in a neutral performance, 0 perf AUC, which is at least not negative. Section summary. We compared the performance of naive sequential fine-tuning, our selective sequential fine-tuning procedure, and an oracle checkpoint selection algorithm in our benchmark. The oracle algorithm selects the best fine-tuning path in hindsight and serves as an upper bound for our selective model. Our results show that our selective procedure can leverage positive transfer regardless of task order, although it may lag behind the oracle in some cases. Additionally, negative transfer effects are rarely compounded when there are 2 negative or negative and neutral intermediate tasks. Section 7. Limitations and Challenges. In Section 7, we discuss the limitations and challenges of our research. Although our work serves as a foundation for examining robust and efficient continual learning, there are still several areas that need improvement. Primarily, our study is limited to T5 base models using basic optimization methods. The only transfer method we investigate and utilize is through parameter initialization, without taking into account the efficiency of space usage, such as minimizing the total number of parameters saved across all tasks. This means our selective checkpoint initialization approach has an advantage in this specific context. Moreover, our oracle, or predictive model, is only assessed based on this approach. Other methods employing different knowledge transfer models might yield better results. We also acknowledge that noise, or random variations, can be introduced through stochastic effects in stochastic gradient descent, SGD, such as variations in learning rates and batch sizes. This can lead to some confusing results, particularly when we're aggregating over log updates, which tends to favor early performance. This effect is more pronounced in some tasks than others. Lastly, as the number of tasks we consider increases, our selective classifier might be more susceptible to identifying a high number of false positives, or incorrect identifications. Without employing calibration techniques that account for multiple testing, the selective classifier might increasingly select poor checkpoints. Section summary. The limitations and challenges of our work include the restriction to T5 base models with simple optimization routines, the focus on parameter initialization as the only method of transfer, and the lack of consideration for space efficiency. Our selective checkpoint initialization strategy is advantaged in this specific setting, and other methods using different knowledge transfer paradigms may perform even better. Additionally, stochastic effects in SGD introduce noise and confounding effects, and as the number of tasks increases, our selective classifier may identify more false positives without calibration techniques.